The greenhouse effect explored. Is water vapor feedback positive or negative? An essential element of the greenhouse effect hypothesis is the positive water vapor feedback hypothesis. That is, if something causes an increase in the temperature, this will cause an increase in the evaporation of water into water vapor. This new humidity will absorb more of the infrared radiation coming off of the ground. This increased absorption of infrared radiation is believed to warm the air even further. This makes the air able to hold even more water vapor, and this results in even more evaporation, which increases the humidity even further, and the cycle repeats. This is called a positive feedback, since water vapor is believed to amplify atmospheric warming. So being curious about the truth of this hypothesis, I designed a simple experiment. It studied the effect of rising and falling levels of humidity on soil and air temperature. And I discovered that the addition of water to a climate system exerts a significant negative feedback against temperature changes day and night. That water vapor has the same relationship to temperature that insulin has to blood sugar. And insulin is known to exert a strong negative feedback against blood sugar levels. And over the course of time, the addition of water to a climate system causes a perceptible drop in yearly mean temperature. Now, the materials that I used for this experiment were a homemade Stevenson screen that had a temperature and humidity data logger in it. That was about 4 foot 10 inches off the ground. I used a thermocouple attached to a data logger to acquire simultaneous soil surface temperatures. I used internet records of yearly mean temperature and humidity readings for several major cities that had contrasting climates. And I used a computer spreadsheet to compile the data and create the graphs that you'll see in this video. The experiment was in 3 stages. The first one, using 38 consecutive days of data harvested from the Stevenson screen and the thermocouple on the ground, I calculated the mean dew point over that 38-day period. I separated the days between those that fell above the mean, which I call the humid days, and those that fell below the mean, which I call the arid days. I then graphed the mean temperature curve of the arid days against the mean temperature curve of the humid days to see what effect the different levels of humidity had on the daily temperature curve. Specifically, I was looking for a positive feedback waveform, which is explained in more detail below. Now, the second part of the experiment, I used 2 consecutive months of data harvested from the Stevenson screen. I calculated the mean daily temperature and graphed it against the mean daily dew point to see what relationship exists between the ongoing temperature changes and the dew point, which, by the way, is an accurate reflection of absolute humidity. Again, I was specifically looking for an indication of positive feedback. For the third part of this experiment, I selected 4 sets of cities with the following criteria: a pronounced difference in their humidity levels. They both needed to be about the same distance from the equator so that they both receive roughly the same amount of sunlight each day throughout the year. And they both needed to be far enough inland to not be affected by sea breezes. So with data that I harvested off the internet, I compared the temperature, adjusted for altitude, to the absolute humidity for these 4 sets of arid versus humid cities, looking for the effect that increased humidity has on the temperature of their respective climates. Asking the question, does increasing the humidity cause a net increase in the temperature, as the greenhouse effect hypothesis, along with the water vapor feedback hypothesis, says that it should? And this is what I found. I found that an increase in the absolute humidity produced a strong negative feedback against temperature changes day and night, in that it inhibited daytime warming and slowed nighttime cooling, as can be seen in this graph, which plots the mean temperature curve of the arid days against the mean temperature curve of the humid days. When plotting the 2 months' worth of daily mean temperatures against the daily mean dew points, as seen in this graph, I found that as the mean temperature rose and fell, there was a strong correlation between rising and falling dew point levels as well, although the change in the dew point lagged behind the temperature changes by about a day. Now, this is the same relationship that rising and falling blood sugar has to rising and falling levels of insulin, in that the waveform of insulin also echoes changes in the blood sugar levels while lagging behind blood sugar in time. Now, since insulin is known to exert a strong negative feedback against rising blood sugar levels, this 2-month-long graph is consistent with humidity being a negative feedback against increasing temperatures. Now, what bolsters this idea is the fact that it rained near the beginning of this 2-month period. And as the soil dried out over time, the humidity levels trended downward while the temperature trended upward, which again is consistent with humidity being a negative feedback against increasing temperatures. The 4 sets of cities that I used in the third part of the experiment for my comparative study between arid and humid climates were Phoenix versus Dallas, Las Vegas versus Knoxville, Tennessee, Death Valley, California versus Huntsville, Alabama, and then Riyadh, Saudi Arabia versus Bogra, Bangladesh. In all 4 of these cases, the more humid climate had a significantly cooler yearly mean temperature than the arid climate. So let's discuss these findings in a little more detail. Before we can identify the signature characteristics of positive and negative feedback waveforms, we need to understand what a feedback is in science. The scientific definition of a feedback is this: when the results of an initial process trigger changes in a second process, that in turn influences the initial one. A positive feedback intensifies the original process, and the negative feedback reduces it. To better understand this scientific definition of feedback, let's look at some well-known examples of positive and negative feedback. The first example that we'll look at is the body's regulation of blood sugar levels through the negative feedbacks exerted by the hormones insulin and glucagon. This graph is a simulated curve of blood sugar levels for about 5 hours after a meal. Shortly after a meal is eaten, blood sugar begins to rise, and in response, the body releases insulin, whose effect is to lower blood sugar. Insulin's effect is called a negative feedback because it counteracts this rise in blood sugar. When the blood sugar begins to drop, the insulin level drops as well. Now, to keep the blood sugar from falling too far too fast and to maintain a basal level of blood sugar between meals, the body releases a second hormone called glucagon, and its effect is opposite that of insulin. It works to slow falling blood sugar. Insulin slows rising blood sugars, and glucagon slows falling blood sugars. So even though the action of glucagon is opposite that of insulin, they're both negative feedbacks because they counteract changes in blood sugars rather than amplify them. Again, if blood sugars are increasing, insulin kicks in to slow down that increase. If blood sugars are decreasing, glucagon kicks in to slow the decrease. As you can see in this graph, a second process that creates a negative feedback can either be in phase or out of phase with the initial process. What makes feedback positive or negative is not the direction of its force, but whether or not it inhibits or amplifies the change that triggered it. In nature, negative feedbacks create stability, while positive feedbacks create instability. These are 2 generic graphs of positive and negative feedbacks. One is ascending, the other is descending. The positive feedbacks are in red, and the negative feedbacks are in blue. And as you can see, positive feedback amplifies the change, while negative feedback attenuates the change, regardless of whether the direction of change is up or down. Now, if these graphs were of temperature curves, then a positive feedback could either cause greater warming or greater cooling, depending upon the time of day. For example, it's said that water vapor feedback is positive because it is believed to amplify warming. If an increase in humidity were shown to amplify nighttime cooling, that would be a positive feedback as well, because it would amplify the temperature change already occurring, cooling. Now, I only bring this up because, ironically, the most common example offered as proof that water vapor feedback is positive is the fact that humid nights cool more slowly than arid nights. And this is actually a negative feedback against nighttime cooling. Now, this is more than just a matter of semantics, because remember, in nature, negative feedbacks bring stability, while positive feedbacks bring instability. If we mislabel a negative feedback and call it a positive feedback, we might be led to believe that the addition of humidity to a climate system will destabilize it. Let's turn our focus to positive feedback for a minute. As you can see in this graph, examples of positive feedback have a distinctly different look. They have a signature exponential curve that usually ends abruptly because of some terminating event. One example of positive feedback in nature can be seen in labor pains of childbirth. Known as the Ferguson reflex, each contraction stimulates a higher release of the hormone oxytocin, which increases the strength and frequency of the contractions. The terminating event, of course, is the birth of the child, at which time contractions abruptly stop. Another example of positive feedback is the squeal heard through a PA system when the microphone is placed too near the speaker, and the sound from the speaker is picked up by the microphone and fed back through the amplifier. Everyone hears an abrupt, loud squeal, which terminates just as abruptly when the speakers blow. Another example of positive feedback is the growth in the debt of a company whose expenses are consistently greater than its receipts year after year. Its debt will continue to grow exponentially until it's terminated by bankruptcy. So comparing these two graphs, the signature trait of positive feedback waveform is that it's very spiked compared to the rounded waveform seen in negative feedback. Now, departing from this classical scientific definition of feedback, contemporary literature defines positive water vapor feedback one-dimensionally and implies that positive water vapor feedback always results in warmer temperatures. And when you see a counter-argument that asserts that water vapor feedback is negative, the term is also used one-dimensionally and implies that a negative water vapor feedback always results in cooler temperatures. Again, positive feedback will only result in warmer temperatures and negative feedback will only result in cooler temperatures if the basal temperature is already trending warmer, as it does every day from sunrise to mid-afternoon. If the basal temperature is trending cooler, as it does predictably and repeatedly every night, then positive feedback would make the temperature even cooler. And negative feedback would result in a warmer temperature at the end of the night. So, using this understanding of the scientific definition of feedback, let's take a look at the results of my experiments, starting with the study of the effect of humidity on the daily temperature curve. Again, for 38 days, I measured soil and air temperatures along with a dew point every 30 minutes. I averaged those readings to produce this graph of daily temperature and dew point curves. The bottom green line is the dew point, which again is a good reflection of absolute humidity. And as you can see, the only time during the day that evaporation takes place and the absolute humidity increases is between sunrise and early afternoon. If positive water vapor feedback that results in higher temperature happens, it happens during this period of the day, since an essential element of the positive water vapor feedback hypothesis is rising absolute humidity levels coupled with rising temperatures. For the rest of the day, both the temperature and humidity are in decline. A positive feedback during that time would accentuate the rate of cooling. So the first thing that I did was to find the 38-day mean dew point and divide the days up between those that fell above the mean, the humid days, and those that fell below the mean, the arid days. I then averaged their respective daily temperature curves and plotted these curves on a graph. And in this graph, the red line is from the arid days and the blue line is from the humid days. The light blue line is the average dew point curve from the humid days, and the orange line is the average dew point curve from the arid days. Since the hypothesis that we're testing, the positive water vapor feedback hypothesis, requires an increasing absolute humidity coupled with a rising temperature, and this only occurs between sunrise and early afternoon, I focused my attention on that period to see if increasing the humidity on humid days amplified the rate of temperature increase during that period. Here's the graph. In this graph, the red line is the soil temperature on the arid days, and the blue line is the soil temperature on the humid days. The light blue line is the dew point on the humid days, and the orange line is the dew point on the arid days. Opposite from the positive water feedback hypothesis, what we see is that as the humidity rises, the rate in soil warming decreases. This is a strong and pronounced negative feedback. Again, as the level of humidity increases in the atmosphere, the rate of soil warming decreases during the period of the day when evaporation happens, thereby slowing the evaporation process. If humidity exerted a positive feedback on soil temperatures, then the rate of soil warming from sunrise to early afternoon would increase as the humidity increases. But it doesn't. it decreases. Now here are the same readings in bar graph form. The two bars on the left are from the arid days. The two bars on the right are from the humid days. The red bars are the mean temperatures, and the blue bars are the mean absolute humidity readings. Again, these are the averaged readings in temperature and humidity from sunrise to mid-afternoon. As you can see, as the humidity increases, the temperature decreases during the period of the day when evaporation is occurring, during the only part of the day which positive feedback would result in higher temperatures. Again, this is a clear and distinct negative feedback. To complete our analysis of the effect of humidity on the daily temperature curve, let's look at the rest of the day, from about 2 p.m. until sunrise the next morning. The blue line again is the soil temperature on the humid days, and the red line is the soil temperature on the arid days. The light blue line is the dew point on the humid days, and the orange line is the dew point on the arid days. As you can see, an increase in the absolute humidity is accompanied by a delay in nighttime cooling. This again is a negative feedback, as it counteracts the more rapid cooling trend seen on arid days. Now those were graphs of soil temperatures, and if we look at air temperatures, we see the same negative feedback day and night. Now I feel that something needs to be clarified at this point. I'm not asserting that the negative feedback seen in the above graphs are the effect of water vapor alone, because water vapor doesn't exist in isolation. Higher humidity in the air is accompanied by more cloud cover. This shades the earth during the day and creates temperature inversions at night, which slows or stops the upward convection currents at night. More clouds also mean more rain or snow, which further cools the soil since precipitation falls from an altitude where it's colder than the ground, and this cold precipitation cools the soil by direct contact. More humidity also usually means there's more water in the soil, which has at least two effects on temperature. One, more water is available to cool the soil through evaporation, and increasing the water content of soil increases its specific heat, which will by itself dampen the swing in diurnal temperatures that one sees in dry climates. These graphs manifest the net effect of all of those forces combined. And all of those forces combined, as we can see, produce a pronounced negative feedback against temperature changes day and night. Now, it's beyond the scope of this particular video to sort out the contribution that each of these separate forces makes to the net effect on temperature. I'm simply asking the question, what effect does the addition of water to a climate system have on the overall temperature of that climate system? The greenhouse effect hypothesis combined with the water vapor feedback hypothesis asserts that the addition of water to a climate system should cause a marked increase in the temperatures within that climate system, since the addition of water brings with it increased humidity, and water vapor is said to trap heat in the atmosphere. As we've seen, the addition of water to a climate system manifest by a higher absolute humidity causes less warming during the day coupled with less cooling at night. But we don't know if over time whether or not these opposing feedbacks cancel each other out, or if one or the other is dominant and swings the mean temperature higher or lower. So let's expand our time frame to 2 months and look at the daily mean temperature versus dew points over that period of time. So here's a graph of the daily mean temperatures versus the daily mean dew points over a 2-month period. The red curve is the daily mean temperature, and the blue curve is the daily mean dew point. As you can see, as the temperature rose and fell, the dew point rose and fell as well. If I may, I'd like to make a couple comments about this graph. First, although there's a strong correlation between the waveform shapes of these two trends, the temperature changes precede the dew point changes by about 24 hours. This demonstrates that the temperature is driving the humidity level, as has been observed in other studies, and which is the first premise expressed within the water vapor feedback hypothesis. As the temperature goes up, more water is evaporated into water vapor, and as the temperature goes down, more water vapor is condensed back into water. Now, conventional wisdom asserts that this correlation between temperature and dew point increases and decreases proves that water vapor feedback is positive. Yet we see the exact same pattern of correlation present in a negative feedback. As we've already discussed, rising blood sugar levels are followed by rising insulin levels, and dropping blood sugar levels are followed by dropping insulin levels. And insulin is known to exert a profound negative feedback against rising blood sugars. Therefore, this graph is consistent with the presence of water in a climate system being a negative feedback against increasing temperatures. Now, it just so happened that there was some rain near the beginning of this 2-month period. And as you can see, as time passed and the soil dried out, the level of humidity in the air trended downward as the temperature of the air trended upward, even though the rise and fall correlation remained present. Now, this is an inverse relationship and is again consistent with negative feedback rather than positive feedback. Now, the fact that as the soil dries out, the general level of humidity drops demonstrates an important reality. Water vapor feedback cannot exist where there is no water in the soil, such as the dry sand in an arid desert. So, what we'll do next is compare a few arid climates with a few humid climates to see if the presence of water in these respective climate systems has a warming or a cooling effect. Now, I did this comparative study under the assumption that if water vapor traps heat in the atmosphere, then it'll trap the heat in the location where the humidity is. That is, the humidity in Dallas, Texas, does not trap heat in Phoenix, Arizona. Whatever heat is trapped in Phoenix will be the doing of the humidity that's present in Phoenix. So let's start by comparing Phoenix to Dallas. They're both about the same distance north of the equator and therefore receive about the same amount of sunlight every day throughout the year. They're also both inland far enough not to be affected by sea breezes. Since Phoenix only receives about 7 inches of precipitation annually and Dallas receives about 35 inches, the air in Dallas is much more humid than the air in Phoenix. If the greenhouse effect hypothesis is true and the amount of heat that the atmosphere traps increases as the humidity increases, then the mean annual temperature in humid Dallas should be much higher than the mean annual temperature in arid Phoenix. So let's take a look. In this chart, the bars on the left are from Phoenix, the bars on the right are from Dallas. The blue bars are the yearly mean absolute humidity in grams per cubic meter. The red bars are the annual mean temperatures adjusted for altitude in degrees Celsius. Now, these numbers are from the National Weather Service, and as you can see, even though Dallas is significantly more humid than Phoenix, Dallas is nevertheless significantly cooler on average than Phoenix. Let's take a look at Las Vegas, Nevada, and compare it with Knoxville, Tennessee. Again, these cities are both about the same distance north of the equator, so they receive about the same amount of sunlight every day throughout the year. And they're both inland far enough not to be affected by sea breezes. Las Vegas only receives about 4.5 inches of rain annually. Knoxville receives about 48 inches of precipitation. Consequently, the air in Knoxville is much more humid than the air in Las Vegas. If the greenhouse effect hypothesis is true, and the amount of heat that the atmosphere traps increases as the humidity increases, then the mean annual temperature in humid Knoxville should be much higher than the mean annual temperature in arid Las Vegas. So let's take a look. Again, in this chart, the bars on the left are from Las Vegas and the bars on the right are from Knoxville. The blue bars are the mean absolute humidity in grams per cubic meter, and the red bars are the mean annual temperatures adjusted for altitude in degrees Celsius. Again, these numbers are taken from the National Weather Service, and as you can see, even though Knoxville is significantly more humid than Las Vegas, Knoxville is nevertheless much cooler on average than Las Vegas. Let's take a look at Death Valley, California, and compare it to Huntsville, Alabama. Again, these places are both about the same distance north of the equator and therefore receive about the same amount of sunlight every day throughout the year. They're also both inland far enough not to be affected by sea breezes. Now, Death Valley only receives about 2.4 inches of rain annually, while Huntsville receives about 57 inches. Consequently, the air in Huntsville is much more humid than the air in Death Valley. If the greenhouse effect hypothesis is true, and the amount of heat that the atmosphere traps increases as humidity increases, well, then the mean annual temperature in humid Huntsville should be much higher than the mean annual temperature in arid Death Valley. So let's take a look. In this chart, the bars on the left are from Death Valley, the bars on the right are from Huntsville. The blue bars are the absolute humidity in grams per cubic meter, and the red bars are the mean annual temperatures adjusted for altitude in degrees Celsius. As you can see, even though Huntsville is significantly more humid than Death Valley, it nevertheless is much cooler on average than Death Valley. Let's look at one more example from the international arena. Let's compare Riyadh, Saudi Arabia to Bogra, Bangladesh. Again, these cities are both about the same distance north of the equator and therefore receive about the same amount of sunlight every day throughout the year. They're also both inland far enough not to be affected by sea breezes. Riyadh only receives about 3.7 inches of precipitation annually, while Bogra receives about 63 inches. Consequently, the air in Bogra is much more humid than the air in Riyadh. If the greenhouse effect hypothesis is true, and the amount of heat that the atmosphere traps increases as the humidity increases, then the mean annual temperature in humid Bogra should be much higher than the mean annual temperature in arid Riyadh. So let's take a look. In this chart, the graphs on the left are from Riyadh, and the bars on the right are from Bogra. The blue bars are the absolute humidity in grams per cubic meter, and the red bars are the mean annual temperatures adjusted for altitude in degrees Celsius. As you can see, even though Bogra is significantly more humid than Riyadh, it is nevertheless noticeably cooler on average than Riyadh. Now, these observations might seem counterintuitive, since we often perceive humid climates to be warmer than arid climates. But as we've seen, this is just a sensory illusion. Since our bodies are water cooled through perspiration, which is more efficient when the humidity is low, people who move from Dallas to Phoenix or from Knoxville to Las Vegas think that they're moving to a cooler climate. But they're not. It just feels cooler. So what does this all mean? Well, although it's true that warmer temperatures do create higher humidity in climates where there is water in the soil to evaporate, that greater humidity demonstrably does not lead to even more warming. Quite the contrary. As we've seen, the presence of water in a climate system exerts a negative feedback on temperatures both day and night, which stabilizes the wide diurnal swings in temperature that we see in arid climates, and over time causes humid climates to be somewhat cooler on average than arid climates. You know, in this sense, water acts as the Earth's thermostat, not its heater. The observations made in this video also falsify any notion that there could ever be runaway global warming driven by positive water vapor feedback, where the oceans evaporate into the atmosphere and all life on Earth perishes. Why? Because water feedback is negative feedback. And if it were going to happen, it already would have. One final thought. These empirical observations do not deny the fact that the various climates around the world continue to experience variations over time, but rather they demonstrate that the presence of water on our planet continues to act as a stabilizing force as it exerts negative feedback against temperature changes up or down.